Okay, welcome to today's class. We are going to continue on with Chapter 3 material, and if all goes as planned, we should finish Chapter 3 today, which will be the end of the exam material. If we don't get through that, we'll clean it up next time. That'll give you at least a week to prepare for the first exam, which starts on the 21st of February, I believe. That's the right date. All right, so we'll go through with that. There's no new announcements today. It's just the exam review session I told you about last time. I'll remind you guys next week about that, and the sheet for that we're going to go over, the practice exam that I'll cover during that review. I plan to post that this afternoon or tomorrow, so that should be ready to go soon. All right, so let's get right back into what we were continuing with, what we ended with last time, where we were talking about how to draw Lewis structures. So I broke it down into a step-by-step approach where there's at least 4 or 5 steps depending on how you count them. And we got through the first 3 of those last time, where we were able to distribute all of the valence electrons as either bonding pairs between the central atom and the outer atoms, or as non-bonding electrons, first on the outer atoms, then any leftovers on the central atoms. So we went through all that last time, so let's just quickly review that. So we did PCl3, which we counted has 26 valence electrons. So remember, the valence electron counting comes from each atom on the periodic table. The group number tells you the number of valence electrons that atom will contribute. So for PCl3, we start by, in every case, we start by drawing the central atom with single bonds to the outer atoms. We complete the octets of the outer atoms first. Those will always have complete octets unless they're hydrogen. So that's PCl3, but that's only 24 of our electrons with 3 octets. We have 26 to use, so any remaining go on the central atom. So that was where we ended up with PCl3. And then for NO3-, we came up with this structure initially. So this has 24 valence electrons. We have to remember to include the negative charge as an extra electron. And so NO3- comes out like this. We complete the octets on oxygen first. And you should always have enough electrons to complete the octets of the outer atoms. But here we've already used all 24. We don't have any more left. So this, at that point, is where we stopped. Now, we're not necessarily done, as we'll see, but we're done adding electrons. We might just have to redistribute them. And then for IF5, this one has 42 valence electrons, 7 from each of the halogen atoms in the structure, iodine at the center, 5 fluorine single bonded, octets on all the fluorines, and then we left 2 more for the central atom. So the 5 octets for fluorine is 40 of our 42, 2 more go on the central atom. So as you practice these types of structures, these first few steps should come very easily and very naturally, where you won't even have to necessarily think about each step one by one. You'll kind of progress through them like I did there in pretty rapid succession. But then once you get to this point, you have to evaluate your structure and see if it's done or see if there's more that you should do with it. Now, the one thing that you're always going to want to think about when you're drawing a Lewis structure is the octet rule. So the octet rule states that with few exceptions, the atoms in a Lewis structure are going to have 8 total electrons around them, either from the bonds that count as 2 electrons each, or from the lone pair electrons that we count individually. And we want to make sure that that's true for all the atoms in the structure, with few exceptions. Hydrogen, of course, being the one that's always going to be an exception. And then we talked about beryllium and boron last time, Be and B, the 2 symbols, being 2 elements where you're not going to typically see complete octets, and then in those cases you're going to leave it as is. But in every other element we're dealing with, we want to have those 8 electrons, or in some cases more than 8 electrons is fine too, as we discussed. So if we look at these 3 structures, in PCl3, the octets of all the atoms are maintained, because each chlorine has a single bond and the 3 lone pairs for a total of 8, so 6 non-bonding electrons, 2 bonding electrons for a total of 8, and we completed the octet of chlorine, so that should be true. And then if we look at our central atom, the central atom right now has 2, 4, 6 electrons that are shared in bonds, and then 2 more as a non-bonding pair, so that's also a total of 8. So this one, the octet, we're good to go. But then if we go to nitrate here, NO3-, what we find is that the oxygen atoms are all complete octets. We already just did that. But then the central atom in this case only has 2, 4, 6 electrons as drawn now. It only has 3 single bonds, 2 electrons each. So this one is going to be an incomplete octet as drawn. And again, every Lewis structure you draw, you want to make sure the octet rule is followed. There's really going to be, as I said, very few exceptions to that. And then for IF5, what we see is each fluorine is an octet. The outer atoms should be, if you did the first couple steps right. And then our center atom has 2, 4, 6, 8, 10, 12 electrons, 5 bonds for 2 electrons each, plus the 2 lone pair electrons. So this one expands the octet. But again, that's going to be fine if your central atom is in the third row of the periodic table or below. So iodine is down there in the 5th or 6th row, I think, probably 6th row, and that one's going to be fine to expand the octet. So this one has 12 valence electrons around the central atom. But anytime you have an incomplete octet on your central atom, unless it's one of those 2 exceptions, beryllium and boron, then we need to do some more things to it. So here's how we're going to deal with incomplete octets on the central atom. So as of now, we only have single bonds, but if your central atom has an incomplete octet, that's the time when you know that you're going to need to draw one or more multiple bonds to make sure that the octet on the central atom is completed. So with this structure here that we've since drawn for NO3 minus as our starting point, and I guess to be complete, we should indicate that there's an overall negative charge. That's just a little bracket with a minus indicating that the whole thing is negatively charged. And this nitrogen atom here, as we said, only has 6 electrons, and that's not what nitrogen wants to be. Nitrogen always wants to have a complete octet, exactly 8 electrons. So the way we do this is we might be tempted to just slap on a double bond, but we can't do that quite simply as that because we can't add more electrons to the structure. This already has all 24 valence electrons that we counted up, so we can't add electrons, but what we can do is we can remove one of the lone pairs from the outer atoms and turn it into a double bond. All right, so we're just redistributing. We're not adding new electrons because that would cause problems with the octet rule on oxygen, and it would add additional electrons beyond what we have in this structure. It's only 24. So what we're going to do is we're going to take one of these lone pairs from oxygen, just choose whichever one you want, and we're going to change that into a bonding pair as now a double bond between the nitrogen and that oxygen. So we would draw this now, where now this lone pair only has this oxygen only has 2 lone pairs or 4 non-bonding electrons. We've taken one of those pairs away and made it into this new bond here between nitrogen and oxygen. So this structure here for NO3 minus would follow the octet rule. Every oxygen atom still has 8 valence electrons. The one that has the double bonds, it's again a different distribution. So now it has 4 from the bond in the double bond and then 4 as lone pairs, but still a total of 8. And our nitrogen central atom now has 2, 4, 6, 8, 4 bonds, total of 8 electrons. So in this structure that I've drawn here, the octet rule is completely satisfied. Okay? Now there's one more thing we're going to do with this structure a little bit later that I'll show you, but for now this is a good Lewis structure for NO3 minus. Octet rules are followed, nothing is in violation of that, and so this would be an acceptable structure for that. Now, the last thing that you sometimes have to do in Lewis structures, and typically in this situation for formal charges, we will usually specify whether this is something you should consider or not. So formal charges is a little bit of an accounting trick that we play when drawing Lewis structures, as I'll show you, which helps us evaluate whether the distribution of electrons and whether the number of multiple bonds is reasonable for that structure. But in real life, formal charges don't really matter that much. The octet rule does matter a lot, but formal charges not as much. And in some situations, formal charges is important. In some situations, is not. So on exam questions or homework questions, if we want you to consider a formal charge, we will typically specify that that's the case. We'll say use formal charges or draw the structure that minimizes formal charges, something like that. So you'll look for that key word to know that it's a situation where formal charges actually matters in that type of problem. But let's define what it is and figure out how to determine it. It's not terribly difficult to do. So the definition of formal charge, again, it doesn't have a real physical meaning. It's just a way of accounting for the electrons in a Lewis structure. And so when you draw a Lewis structure, the formal charge is going to be defined for every atom in the structure. And it's going to be that the charge that atom would have if the bonding electrons were shared equally. So it assumes that we have perfect covalency between all the bonded atoms, which again we know is not rigorously true in a physical sense because we have different electronegativity values. We talked about that last time. And because of the different electronegativity values, electrons are often not shared equally. But the formal charge assumes that the electrons are shared perfectly equally, and it counts them up that way. Again, dividing up the bonding electrons exactly in half between the two atoms that are bonded. So what should happen then, once we calculate formal charges, which I'll show you how to do in a second, if you sum the formal charges over the entire molecule or ion, so every atom is going to have a formal charge, you sum them all up for every atom, that will equal the total charge of the molecule or ion. So if it's a neutral molecule, which is most of the ones that we'll deal with, then the sum of the formal charges has to equal 0. If it's an ion with a net charge like NO3-, which has an overall -1 charge, the sum of the formal charges has to be equal to -1. So when you're calculating formal charges, if we ask you to do that, then it's a good way to check yourself. If you calculate the formal charge for every atom in the structure, add them together, that should equal the overall charge for the entire structure, whether it's 0 for a neutral molecule or charged because it's a polyatomic ion. So the way that we calculate it is, again, it's going to be for every atom in the structure. So it doesn't apply to the entire structure, it applies to each atom in that structure. So the formal charge on an atom in the structure is given as follows. There's a few different ways of writing this, but here's the way that I like to count it up. So you're always going to start with the number of valence electrons that that atom provides. So again, we count that up at the beginning. So each atom is going to contribute a certain number of valence electrons to the structure based on where it is on the periodic table. Its group number on the periodic table tells us that. So that's what we're going to start with, and then we're going to subtract from that the number of bonds that that atom has. And again, where this comes from is formal charge is assuming that that the bonding electrons are shared perfectly equally. So this is 1/2 times the number of bonding electrons is another way of thinking about that. Because again, for formal charge, we're taking those bonding electrons and we're dividing them equally between the two atoms that are bound. So each bond is going to count as 1 electron in this case. 1 electron that belongs to that atom, the other one belonging to the other atom that it's bonded to. So that's how we count that. And then the second thing we subtract is the number of non-bonding electrons around that atom, where we count each lone pair of electrons, each electron in that individually. All right, so each lone pair electron, each non-bonding electron counts as belonging exclusively to that atom. It's not shared between the two, obviously. So that's how we calculate formal charge. So it's just 3 things you have to consider: valence electrons, and then you look at the structure that you have drawn, and you just count the number of bonds that an atom has, and you count the number of non-bonding electrons that an atom has. So for that particular structure, you just count those up as it's drawn. So let's go through the ones we've been doing then in a little bit here. But first, let's talk about, why do we use formal charges, or how do we use them? So typically, in most cases, the structure that you draw, the best Lewis structure that you can draw for a molecule or ion, is going to minimize formal charges. Now, as we said, sometimes this is more important or less important depending on the situation, so we'll typically specify whether you should do this or not in a problem where it matters. But typically speaking, if you have a neutral molecule, the best Lewis structure is normally going to have 0 formal charge, or at the very least, it's possible to draw a Lewis structure that has 0 formal charge in most cases. This is not exclusively true. But again, if we ask you to minimize formal charges when drawing the Lewis structure, this is something that we could specify that you need to do in some problems. If we say minimize the formal charges, if it's a neutral molecule, you should strive for a structure that has no formal charges on any of the atoms, basically 0 for all the atoms. In some cases, that's not possible, as we'll see, but in most cases it is. And then if you have ions, the polyatomic ions like NO3- or other ones that we could give you, you're going to have a formal charge somewhere, right? Because the sum of the formal charges equals the charge of the ion, so there has to be a non-zero formal charge somewhere. You can't have all 0 formal charges in an ion, or it wouldn't be charged. So you have to have a charge somewhere, but what you want to do is you want to minimize the number of formal charges that you have and their magnitude. So typically speaking, again, I don't like to speak in absolutes because everybody can find exceptions here and there, but typically speaking, you're not going to have +2 or -2 formal charges in a structure, especially in the case where you're trying to minimize those formal charges. That's not usually going to be required. So you want to avoid +2 and -2 formal charges. Typically, you'll just have some combination of +1 and -1, if anything. And you don't want to have too many formal charges. If every atom in the molecule or every atom in the structure has a formal charge, then you probably can reduce that in some way in most cases. Okay, so that's kind of the things you're going to do, and we'll see examples of this to understand how it works. So if you want to minimize formal charges, if that's what we're asking you to do, and there's a couple things that you can do to help with that, and usually what you're going to see is if you have a positive and a negative formal charge right next to each other. So one atom is negative, one atom is positive, and those two are bonded together. You can get rid of both of those by drawing another multiple bond between them. So if you have a plus and minus formal charge on adjacent atoms, atoms that are bonded to each other. So if that's the case that you have, which is often going to be true in structures where the formal charges are not minimized. So you have a plus and minus formal charge on adjacent atoms. They can be canceled by drawing a double bond between them. Now, Ken, you can't just add in a double bond because that's going to mess up how many valence electrons are in the structure. But what you do is you take a lone pair from the atom that's negatively charged in a formal charge sense, and you convert that into a double bond between the two. All right, and again, we'll see examples of that. But of course, when you're evaluating formal charges, even in the situation where we ask you to consider that, if it's important, you have to still remember the octet rule. So the octet rule always reigns supreme, because if you're going to minimize formal charges, you often would have to expand the octet on the central atom, and you remember you can only do that, exceed the octet rule, if the atomic number is greater than 10. All right, so if we ask you to, minimize formal charges, but the structure has nitrogen in the center, which is atomic number 7, you don't want to go beyond 8 electrons to do that. You still need to be mindful of the octet rule. So don't just willy-nilly start adding a bunch of double bonds to get rid of your formal charges. You have to make sure you're not violating the octet rule in situations where that is going to be a consideration. Okay, so octet rule, don't forget about that in structures where it's not possible to. So if we go back to the 3 structures that we've drawn, which I didn't want to draw again, so here they are, let's evaluate the formal charges in these structures and see if there's anything we can do to minimize them. So if we look at PCl3, we're going to calculate formal charges for every atom in the structure. We have a phosphorus at the center, and then we have 3 chlorines. All chlorines we should recognize are identical. They all have 1 bond, and they all have the 6 lone pair electrons, or 3 pairs. And so we're going to only need to calculate it for 1 chlorine, and that'll get the same. They'll be the same for all 3 chlorines because they're identical. They all have the same arrangement of electrons. But let's do it for each atom then. So for phosphorus, if we go to the periodic table and remind ourselves how many valence electrons it has, remember at the very beginning of this process for drawing a Lewis structure, we would count valence electrons. So now we're going to go back to that here when we're evaluating formal charges. Phosphorus is group 5A. So it's going to have 5 valence electrons as a neutral atom, and then chlorine was in group 7A, so it was 7. So those are the numbers we're going to start with when calculating formal charge as well. All right, so that's the number of valence electrons. I'll just write that down so we don't forget, 5 and 7 for phosphorus and chlorine. And then to calculate formal charge, remember there's 2 things we subtract from that. We subtract the number of bonds that atom has. Phosphorus right now has 1, 2, 3 bonds in the structure, 3 single bonds. So we subtract that. And then we subtract the total number of non-bonding electrons on that atom. Phosphorus here has 1 pair, or a total of 2 non-bonding electrons as drawn. So 5 minus 3 minus 2 is 0. So that means in this structure, phosphorus has 0 formal charge. Now, because this is a neutral molecule, if we did our job right, chlorine should also be 0, because it's the sum of the formal charges has to be 0 for a molecule that doesn't have any net charge in it. So for chlorine, if we look at the calculation, each chlorine has 1 bond. We're doing it for each individual chlorine atom here. So they brought in 7 valence electrons each. They each have 1 bond, and they have 2, 4, 6 of those non-bonding electrons that we added in earlier. So 7 minus 6 minus 1 is also 0. So this structure, in addition to following the octet rule, has no formal charges on any of the atoms. They're all 0. And so this would be the best Lewis structure we can draw for PCl3, and anything else you do would basically ruin the structure. You don't want to try to draw any double bonds in this case, where you're going to start introducing formal charges, which is not what we want to do. Okay, so this is the best structure because all the atoms have 0 formal charge. And then for IF5, we'll do this one next because it's also the slightly less complicated one. So for IF5, again, we have 2 different atoms in the structure, iodine and fluorine. We have 5 fluorines, but each of them is identical. If you look again, they all have a single bond. and 3 lone pairs. So all the fluorines are identical, and then we have the central iodine that we have to calculate as well. So I and F are both group 7 elements. They're all both in the halogen series, so they're going to bring in 7 valence electrons each. And if we calculate it for the central atom right now, this iodine at the center has 1, 2, 3, 4, 5 bonds. So that's the first thing we subtract. 5 bonds, or 1/2 times the number of bonding electrons, which is 10 bonding electrons, 5 that belong to iodine when they're shared equally. And then it has 2 non-bonding electrons, 1 pair also on the central atom. So this structure has 0 formal charge for the central atom iodine. And then if we calculate it for each fluorine, again, there's 5 identical fluorines, so this formal charge would apply to all 5 of them. Each fluorine brought in 7 valence electrons. It has 1 bond, and then it's going to have 2, 4, 6 non-bonding electrons. That also gives us 0 once again. All right, so this structure also has 0 formal charges on every atom. It's charge neutral, so that's the best structure we can draw. And as you do this more and more, you'll start to see some patterns. We can hopefully see one already. If you have a halogen, fluorine, chlorine, bromine, iodine, as an outer atom, which is a pretty common situation, they're going to typically always have 1 bond and 3 lone pairs as an outer atom, and that will minimize the formal charge on those atoms. So you'll start to see patterns as you do this that'll help you more quickly draw the Lewis structure and more quickly realize when there's something about it that might not be quite right. So that's one pattern that we've seen right now. If we go to nitrate, this is the slightly more complicated one, because in this case we have the nitrogen at the center, but we have 2 different arrangements for the 3 oxygen atoms. So 2 of the oxygen atoms, these 2 that I'm showing here at the bottom, have 1 bond and 6 lone pairs, 6 non-bonding electrons, 3 lone pairs. But this oxygen up here, where we drew the double bond, has 2 bonds and 2 lone pairs. So the arrangement of electrons is different, so we have to calculate those separately for each of those 2 different types of oxygen atoms. So to keep it straight, we'll call these ones oxygen A. They're the ones that have a single bond in the structure. And the one that has a double bond, I'll call oxygen B. So we're going to have to calculate it separately for both of those because they have 2 different arrangements of electrons. So when we do this for the nitrogen, and then oxygen A and oxygen B, A being the one that's single bonded, or the 2 that are single bonded, each being the same, and then B being the one that's double bonded, let's calculate formal charges for these. So for nitrogen, if we go back to the periodic table, just make sure we review that real quick. So nitrogen is also group 5A, so it had 5 valence electrons originally as a neutral atom. Oxygen is in group 6 right next to it, so each oxygen should have 6 valence electrons. So that's going to be the starting point for all of them. That's just determined by the identity of the element. 5 for nitrogen, 6 for each oxygen. But then we have to subtract the different numbers of bonds and lone pairs they have to be able to calculate their formal charge, and they're all going to be a little bit different, as we'll see. So for nitrogen at the center, in this structure it has 4 bonds. We have to remember to count the double bond as 2 full bonds, so it's 1, 2, and then 3, 4 from the double bond, 4 bonds. And then the nitrogen center atom has no non-bonding electrons, no lone pairs at all, so that's going to be just -0. So we get a +1 formal charge for nitrogen in this structure. And then for oxygen A, the ones that have the single bond, they each have 1 bond, and then the number of non-bonding electrons is 2, 4, 6 for the 3 lone pairs. So 6 minus 1 minus 6 is -1. So our nitrogen at the center is +1. Each of these oxygens is -1 in terms of the formal charge. And then for oxygen B, which has the double bond, oxygen B has 2 bonds, 1, 2 from the double bond, and then it has 1, 2, 3, 4 non-bonding electrons, now just 2 pairs. And this one would be 0. So oxygen B has 0 formal charge. So that's the formal charge arrangement for that ion. +1 in the center, -1s on the outer atoms, the 2 oxygens that are single bonded. Now again, we said earlier that if you have a plus and a minus next to each other, you can cancel them by drawing another double bond. And that's tempting to do here, but this is a situation where we cannot do that, because nitrogen right now already has 8 valence electrons around it. Nitrogen is in the 2nd row of the periodic table, atomic number 7, so nitrogen cannot go beyond 8 electrons. So if you were to draw another double bond here, that would get rid of the formal charges, but it would violate the octet rule on nitrogen, which we absolutely cannot do. So we have to stop here. We have no choice in this case but to leave some formal charges in the structure. +1 in nitrogen, -1 in each oxygen. They add up to -1, which is the overall charge, so that's a reasonable arrangement. That's the best arrangement we can have for this structure. So as I said, you do not want to expand the octet on the central atom. If you're not able to do that, that would be any of those elements in the second row. So the carbon, nitrogen, oxygen, fluorine, those ones you definitely cannot expand their octet. So we have to stop here for this structure. All right, so any questions on how we calculate formal charge? So to give you one more example of how we might use formal charge, and again, it's sort of, actually, we're not quite there yet. Sorry, I'm out of order here. This is fine. So let's talk one last detail about NO3-, which is a concept called resonance. All right. So if the central atom has multiple bonds, and it's sometimes possible to change the bonds to draw the bonds in different ways. So when the central atom has multiple bonds involved, so this concept of resonance only applies to structure where there's some combination of double bonds and triple bonds. You can't have resonance if all of the bonds are single, so that's one thing to keep in mind. We'll come back to resonance in a little bit more detail later on. But at this point, what we can find is that it's sometimes possible to arrange the bonds in different ways. And so if we illustrate it with NO3-, the one we've been working through last time and all of today, we'll see how this comes into play at times. So in other words, what it means is sometimes there's more than one way to draw the structure that follows the octet rule and minimizes formal charge. There's more than one way to draw what you would call the best Lewis structure. And so in reality, the real structure of the molecule is sort of a blend of all of those possibilities. So for NO3-, we drew this structure here as our best Lewis structure. We had to have some formal charges. That was unavoidable, as we saw. But we completed the octet rule on all the atoms, and the formal charges were as minimum as they could be. So that was the structure we drew. Now you may have already been wondering, why did I put the double bond between this nitrogen and this oxygen? Why not put it between these two or these two? In reality, it doesn't matter. The double bond can be drawn between either of them, and the best and most complete way to indicate the full structure of NO3- is to draw what are called 3 resonance structures. So we use these double arrows. So we can move the double bond down to this position, leaving these two as single bonds. So all of these structures are equivalent. They have 2 single bonds, 1 double bond, same number of electrons, same arrangement of formal charges overall. So they're equivalent, but we just move the double bond to the different possible places. And all 3 of these would then be called resonance structures of NO3-. All right. So the last possibility puts the double bond here in this direction. Now, resonance is one of those concepts that's, as a general chemistry student, a little bit hard to wrap your head around exactly what it means. I mean, this is the best way to draw the structure, showing again that the double bond can be in 3 different places, all equivalent to each other. What does it mean about the real, bonding arrangement in this molecule? What it means is that you don't want to think about resonance as, oh, this double bond is moving around, or this double bond is here sometimes, here sometimes. What it really means is that this double bond here is not localized between 1 nitrogen and 1 oxygen, it's delocalized between all 3 of them. So sometimes we can have bonds that are not just localized between 2 atoms, but are actually delocalized over 2 or more atoms. And that concept will make a little bit more sense in the next chapter when we talk about another more advanced bonding theory that we haven't gotten to yet. But what this means is that the real structure for NO3- has 3 identical bonds that are in between a single bond and a double bond. Now, there's no good way to really draw this in a Lewis structure type format, but all 3 bonds are identical, and we can draw sort of dotted lines to indicate that there's 1 bond that's sort of delocalized between all 3. In reality, in chemistry, we draw dotted lines when we want to signify that we have no idea what's going on. In this case, we know what's going on, there's just not a good way to draw it. But we draw it with dotted lines just to indicate that the bond is delocalized between all 3 positions. But you have 3 identical nitrogen-oxygen bonds that are in between a single and a double bond. So it's not that we have 2 single bonds and 1 double bond at any given time, it's that all the bonds are the same and they're in between single and double. So the bond order between nitrogen and oxygen would be, we have 4 shared pairs of electrons, and each of these resonance structures between nitrogen and oxygen is a total of 4 bonding pairs, 1, 2, 3, 4, 2 singles and 1 double. So in each of these there's 4 bonding pairs. There's 3 bonds that they're distributed over. So in reality, each of the bond orders is 1 1/3. So it's possible to have bond orders that are not whole numbers. They don't have to be 1, 2, or 3, but if you have delocalized electrons like this, electrons that move between the different positions, if you want to think about it in those simpler terms, then the real bond order is not 1 or 2, it's in between 1 and 2, and all 3 bonds are identical with that same bond order. So again, it's a hard concept to wrap your head around, but that's really what it means in terms of the structure of this. Another analogy that I've heard for resonance, which may work for you, may not, so if you don't like it, don't blame me. I'm just saying this for the benefit of those that like this analogy. So imagine that you have, so like I'm trying to think of the best way to say it. So a unicorn, right? We all know what a unicorn is, right? It's not a real creature, but it's a one that we can draw out. Think of a unicorn, and the resonance structures that describe a unicorn are a horse and a rhinoceros. So mix a horse and a rhinoceros together, you get a unicorn. So in other words, the real structure of this molecule is all 3 of these structures sort of blended together. It's the sum of all those, or the average of all those, however you want to think about it. So it's not that the structure is this, and then this, and then that. It's that the real structure is sort of a blend of all 3. It's kind of like a unicorn is a blend of a horse and a rhinoceros. But maybe that's a terrible analogy. But if you see it, great. If not, just pretend I didn't say that. Okay, so that's resonance. As I said, we're going to come back to that a little bit, but you have to be aware of the possibility of resonance whenever you have double bonds in the structure that can be moved around to different positions that are equivalent in this way, or sometimes triple bonds can have resonance as well. All right, the last thing we're going to cover with Lewis structures, I think, yes, is this idea here. So just to sort of more clearly define the ways that we're going to use formal charge in this course, just so you kind of have a clearer picture of it. So we saw that in the 3 structures that we drew so far, PCl3, NO3-, IF5, we could calculate the formal charges, that's great, but there ended up not being anything we had to do with the structures on account of the formal charges, because they all already had, once we followed the octet rule for those structures and followed all the previous steps, they already had their formal charges minimized. But let's look at a molecule where the Lewis structure can be drawn in 2 different ways that either follow the octet rule or minimize formal charges. So this is kind of a typical way that we might present problems on homework assignment exams. So again, the situations where the formal charges might matter, we will usually specify one of 2 things. We'll either say, consider the structure that follows the octet rule, or consider the structure that minimizes formal charges. If we don't specify, that likely means that it doesn't really matter which one, that they're all kind of one and the same. But in cases where there's 2 possible ways of drawing the structure, then this is how we would set it up. So if we ask you to draw the structure for SO3 that follows the octet rule, let's go through and count electrons quickly for SO3. So sulfur and oxygen are both in group 6. So all the atoms in the structure are group 6, which have 6 valence electrons each. So we have 1 sulfur, so 6 electrons from the central atom, 3 oxygens, which contribute 6 each. So this would be a structure that has 24 valence electrons. So we want to draw the Lewis structure that follows the octet rule. We're going to follow the same approach that we've been developing, where we start with the central atom sulfur, single bonds to the oxygens, complete the octet of each oxygen. So again, these steps should become second nature as you do them a few times. And so now we take stock of how many electrons we have left to see if any should go in the central atom. So we have 3 oxygens with complete octets at this point, 8 electrons each. 3 times 8 is 24. So this structure here has used all 24 valence electrons, so we can't add any more as lone pairs to the central atom. But if we evaluate where we are right now, this one has only 6 valence electrons, again, as the central atom, 3 single bonds. So if we ask you to draw a structure that follows the octet rule, what that means is that every atom in the structure should have exactly 8 electrons. Again, unless it's one of those few exceptions, hydrogen, beryllium, boron. But if it's anything that's not those 3, if we say follow the octet rule, make sure that every atom in the structure has exactly 8 electrons. So we can't do that at this point with this structure here, that's not true, but the way we can fix that, as we talked about, is we can start introducing multiple bonds. So this sulfur has only 6 electrons, it needs 2 more, so that means it needs to have 1 double bond to add those 2 additional electrons. So again, we're going to take off 1 lone pair, any one that we want, and turn that into a double bond. So the structure that follows the octet rule would look, again, similar to nitrate in some sense, but now it's uncharged overall, where we have 1 sulfur oxygen double bond, 2 that are left as single bonds. In reality, there are 3 resonance structures for this. I'm not going to draw all 3, but we can move this double bond to any of these 3 positions, just like we did before. But this structure here follows the octet rule, so we would just stop there. Okay, we don't want to add any other bonds, because now every atom in the structure has exactly 8 electrons. Each oxygen still has an octet, and now the center atom has 1, 2, 3, 4 bonds for a total of 8 electrons. So if we ask you to follow the octet rule, this is where you would stop. And we can calculate formal charges for this, and we can see now that this isn't the best arrangement of formal charge. So this is one type of problem we would give you, and then we might ask you something about the structure. We're not going to have you draw it, because you can't draw in Blackboard very easily. But we'd ask you, calculate the formal charge in the structure that follows the octet rule, or how many double bonds are there in the structure that follows the octet rule. We want you to draw this structure and then answer some question about it. And you would stop here, because in this structure, every atom has exactly 8 electrons. So the octet rule is followed in this version here. All right, but the other way that we could ask you to evaluate the structure of this molecule is to draw the Lewis structure that minimizes formal charges. That's the other way we could present this. And if we ask you to do that, then again, you would have to draw the structure and then answer some question about it related to maybe formal charges or how many double bonds and things like that. So if we want you to draw the Lewis structure that minimizes formal charges, let's go back to what we just finished with, which is the structure that follows the octet rule. All right, so in this structure, if we want to calculate the formal charges in this version here that follows the octet rule, we have a sulfur and we have 2 different kinds of oxygen atoms. We'll call them again A and B. A being the singly bonded oxygens, B being the doubly bonded one. And when we calculate formal charges for these, what we'll find is that each of these is a group 6 element, so they all brought 6 valence electrons to the structure. For sulfur at the center, we now have 4 bonds, and we have 0 lone pair electrons in sulfur, so that's 6 minus 4 minus 0 is a +2 formal charge for sulfur. Oxygen A, which is singly bonded, same electron arrangement that we saw for NO3 minus for that oxygen that was singly bonded, so it has 1 bond, single bond, and then 1, 2, 3, 4, 5, 6 non-bonding electrons for each of them. So that comes out to -1 for each of those. Oxygen B is a doubly bonded one, so it has 2 bonds from the double bond, 1, 2, 3, 4 as non-bonding electrons. That comes out to 0. So right now our formal charge arrangement is +2, -1, -1. And if we want to minimize formal charges, we should recognize that this is probably not the best way to do it, because SO3 is a charge-neutral molecule. It has no net charge, so ideally we should have 0 formal charge in the structure that minimizes the formal charges. So what we do again is we can, if we have a plus and a minus next to each other, we have a +2 and 2 -1s, we can cancel those out by drawing double bonds between them. And if we look at sulfur here, sulfur is in the 3rd row of the periodic table, so it's okay on sulfur to go beyond 8 electrons if we have to. So we can expand the octet on sulfur. So when we do this, if we want to minimize formal charges, for each of the oxygen atoms that's negatively charged, we're going to take off 1 pair of electrons and turn it into a double bond. And so by doing this, again, every time we make a double bond in this way, we're going to cancel a plus and a minus, so we're going to cancel each -1 formal charge with the +2 on the center by doing that twice. So what we end up with is a structure where we have 3 identical sulfur-oxygen double bonds drawn like this. Sulfur now has a total of 12 valence electrons, 6 bonds, 3 double bonds, but that's okay because sulfur is in the 3rd row of the periodic table, so it's acceptable to do that if we're asking you to minimize formal charges. So this structure here now has no formal charges, because now we have sulfur and oxygen. All the oxygen atoms are identical in this structure, so we just have to calculate it once for oxygen in this case. So sulfur brought in 6 valence electrons. In this structure, it now has 6 total bonds, 3 double bonds. Still no lone pairs. We didn't add any lone pairs, of course, because we don't have enough electrons to do that, but that comes out to a 0 formal charge. And then each oxygen is now the same. They all have a double bond and 2 lone pairs. So double bond is 2 bonds, 1, 2, 3, 4 non-bonding electrons. That also comes out to 0 for each oxygen. Okay, so in this structure here, we have 0 formal charge. So if we're asking you to minimize formal charge, this is how you would want to consider this molecule here. All right, so again, the only time we don't want to play this trick of drawing additional double bonds is if it's the central atom that cannot expand its octet, carbon, nitrogen, oxygen, those ones in the second row there. Okay, but this one is sulfur. We can go beyond 8 electrons, and so we can get rid of all the formal charges by doing this. So if we ask you to draw the structure that minimizes formal charges, this would be the correct one. So in reality, both structures could be correct depending on the context that we're asking you, because there is some controversy in the real world about whether this actually happens. Does this sulfur really form 6 bonds like this to minimize formal charges? In reality, no, but this is just a convenient way of drawing the structure that gets rid of all our formal charges. So that's why in the exam problems where this type of idea is important, we will typically specify what you need to do to make it clear that you should consider either this form of the structure, which has 0 formal charges, or this form of the structure where we have the octet rule perfectly followed. Because this structure that we drew does violate the octet rule because our central atom has more than 8 electrons. All right, so it's a situation where it's okay to violate the octet rule, but it still is a violation. All right, any questions on formal charges? All right, the last thing we're going to do before we move on to the next and last major topic of this chapter is going to be just an example problem on how we sort of evaluate resonance structures. So a resonance structure is any structure where it has the correct number of valence electrons, in technicality can be considered a resonance structure, but some of them are going to be more important than others. Some resonance structures you draw would be so ridiculous in terms of their formal charges and things that you wouldn't even want to consider that. And so if we ask you a question of which is the most important or best resonance structure for a particular molecule or ion, there's a couple of things you want to evaluate. So the first thing is any resonance structure that you draw should have the correct number of electrons. So if you see a resonance structure that's presented to you in a problem and it has the wrong number of electrons, it can't be a valid resonance structure. You can just eliminate that one automatically. So let's count electrons for ClO3- and see how many it should have. So chlorine and oxygen are the 2 atoms, and then it has a negative charge as well. So quickly to go through this, chlorine is group 7. So it has 7 valence electrons. There's 3 oxygens that contribute 6 each. Then we have to remember to add 1 for the negative charge, because there's an overall negative charge. So that's 26 valence electrons for this structure. If we look at these 4 possible resonance structures that we presented, if we look closely at choice D here, choice D has 24 from the oxygens and only 1 on the chlorine for a total of 25. So this structure here only has 25 valence electrons, so this cannot be a correct resonance structure for ClO3-. It has the wrong number of electrons. So 8 for each oxygen is 24, just 1 on the central as a individual non-bonding electron for 25. So this one doesn't have the right number of electrons, so it's gone. Now the rest of these all have the correct number of electrons. They all have 26. So to decide which is the most important, we need to first look at the octet rule and make sure that none of them have fewer than 8 electrons on the central atom. So if we look at A, B, and C here, all of them have at least 8 electrons on the central atom. This one has exactly 8 for choice A, 2, 4, 6, 8. This one has more than 8, but chlorine, we're able to expand the octet. So none of these are in strict violation of the octet rule, or at least not in a way that would cause us to eliminate the structure. So if any of the structures had fewer than 8 electrons on the central atom, that would be one that we could also eliminate. Because again, you're never going to have a valid structure that has fewer than 8 electrons, except for those rare exceptions. All right, but then the next thing we're going to evaluate is formal charge. So when we're evaluating which resonance structure is the most important or the best, it often comes down to evaluating the formal charges for these. So if we look at formal charges for A, B, and C, I'm not going to go through these I'm going to go through these quickly now, but for chlorine here in A, we have 1, 2, 3, 4, 5, 6 total electrons around it, and it brought in 7. So that's going to be +1. Singly bonded oxygens are -1, as we've seen multiple times, and this is 0. So these are the formal charges for choice A, +1 in the center, -1s for the oxygens. Work through those yourself if you didn't quite follow how I got that so quickly, but I don't want to spend too much time on this problem. And then for choice B here, all the doubly bonded oxygens have 0 formal charges. Our central atom in this case is also 0 because now it has 1, 2, 3, 4, 5, 6, 7 electrons around it, and this one's -1. And then for choice C here, all the oxygens have double bonds, which makes them 0 formal charge. That's a pattern that you'll see for oxygen. And our central atom now has 8 total electrons that belong to it, so it'd have a -1 formal charge. So if we're trying to minimize formal charge, again, we want the fewest number of formal charges and the smallest magnitude. So we can get rid of choice A here because it has plus and minus formal charges. The other ones just have a single formal charge somewhere in the structure. So again, when we say minimize formal charge, we want to get rid of ones that have multiple formal charges if possible. So this one has 3 atoms with formal charges, the other 2 only have 1 atom. So that one we're going to get rid of because it has too many atoms with formal charge. But then we have to decide which one of these is the more reasonable structure. We have either the negative formal charge on oxygen or the negative formal charge on the central atom chlorine. Which one is the better one? And it turns out that the one that is the best arrangement is this one here with the negative formal charge on oxygen. Because in general, if you're going to have a negative formal charge in a molecule, it should be on the most electronegative atom. Because remember, the most electronegative atoms are the ones that pull the electrons towards themselves. So if there's a negative formal charge somewhere, it should be on an atom that has high electronegativity. In this case, oxygen is higher electronegativity than chlorine. So when you're evaluating resonance structures, if you have a choice, it's better to have the negative formal charge on the more electronegative atom. So if you're trying to decide where to put the formal charge, in this case we have to have one somewhere because there's a negatively charged ion, put the negative formal charge on the more electronegative atom. And that usually is always going to mean the outer atom. Because again, in almost every structure we draw, the least electronegative atom is in the center, the more electronegative atoms are on the outside. So when you have a choice of where to put a negative formal charge, if it must be there, put it on the outside. That's almost always where it's going to be. I think there's maybe a rare exception to that. The only time you'll have a negative formal charge on the central atom is if you have all single bonds and you have no choice but to have a negative formal charge on the central atom. If you have a choice between putting the negative formal charge on the central atom or the outer atoms, it's better to put it on the outer atoms because they're more electronegative. They pull the electron density more towards them. So choice B would be what we would think is the most important resonance contributor for ClO3-, which is a structure that has 1 single bond, 2 double bonds. In reality, there'd be three resonance structures that describe this equivalently, where the overall bond order is, again, between 1 and 2, in this case, 1 and 2/3. Okay, so any questions on resonance or what we covered today? Yeah?
So for the octet, is it like in most cases that you can go above the 8, but you can't go below the 8?
Yeah, so I mean, technically the octet rule says you can't have anything other than 8. So if we say a structure that follows the octet rule, that's what I said before, you should always have exactly 8. But again, it's possible to violate it's possible to violate the octet rule. So it's not that these structures don't violate the octet rule, it's just that in this case it's okay to violate the octet rule. So when you're evaluating resonance structures, in cases where it's okay to violate the octet rule, then you should look at formal charges instead. So it'll become clearer in the context of as you do the different types of problems. But in this case, because chlorine can go beyond 8 electrons, it's fine to do that when selecting the best resonance structure. In that case, formal charges wins out. If it's a structure like NO3- that we did earlier, where you cannot violate the octet rule in the central atom, then you have to use the octet rule and stop there, because otherwise you're going to be in violation. So that's kind of what I mean by checking the octet rule. So maybe that wasn't totally clear, but as you do more problems, it'll become clear. And I'm not sure if we'll have problems exactly like this on the homework assignments or exams or not, but just be aware that in some cases we use formal charges also to evaluate resonance contributors. All right, anything else before I move on? Okay, so the last major topic for chapter 3 that we're going to cover is nomenclature, which is how to take the formula of a compound and convert it into the name of a compound, or vice versa. So nomenclature is naming compounds. So we're going to do this for basically two major categories of compounds, ionic and covalent. And then within covalent compounds, we're going to have sort of two subcategories, binary covalent compounds and then acids. Okay, so we're going to name compounds and learn how to do that. And there's just rules you have to follow. And this, again, is sort of like learning the language. I updated the table numbers. I had them wrong in the original version of the notes. So if you downloaded your notes before today, these table numbers were reflective of the previous version of the book. But anyway, these numbers are now correct, and the tables are reproduced at the end of the notes today in case you don't have the book or you're confused about which ones you need to know. So these have all the different things we expect you to know for nomenclature. Some of them are fairly simple and obvious. Some of them you have to spend a little bit of time familiarizing yourself with, and I hate to use the word, but you're going to have to memorize some of them. All right, so let's talk about ionic compounds first. So for ionic compounds, when we're naming them, the rules are as follows. So we're going to do, we name the metal first, which is the cation in the formula. And then we do the nonmetal second. So the ionic compounds that we're naming first are going to just have two elements in them, a metal and a nonmetal, and you name the metal first and then the nonmetal. That's the order they come in. And this is going to apply to both the formula and the name. So if you're writing the formula for an ionic compound, it's correct to put the metal first and the anion second, or if you're naming the compound, you do the same thing. Okay, so the cation in an ionic compound, that part of the name, you just take the name of the metal, so we don't change that. So the first part of the name of an ionic compound is just going to state the name of the metal that's in the formula with no change to the format or the ending. So for example, if your formula has Na plus in it, the first part of the name would just be sodium. We don't have to do anything to indicate that it's a sodium cation. We just call it sodium. Or if you have calcium 2 plus, that would just be calcium, and so on. So whatever the metal is in the formula, you just name it. You don't have to change the ending or change anything about it. For the anion, we do a slight change. So we're going to take the root of the name, which comes from the identity of the element, but then we're going to change the ending to IDE. Okay? So if you have F minus in the formula of your ionic compound, when you're naming that, you don't call it fluorine anymore, you call it fluoride. So you put that IDE ending. If you have O2 minus, that comes from oxygen. So you use the root name OX, ox, and then IDE, oxide. So all the anions are going to be named with IDE endings. Or even if it's a 3 minus anion like N3 minus, that becomes nitride and so on. Okay? And usually there's going to be multiple choice. We're not going to have you type out names of compounds very often, or probably not at all, because 120 people in this class would probably spell it 120 different ways, and this is not a spelling class, this is a chemistry class. So typically, nomenclature problems are going to be multiple choice. You have to make sure you pick the correct name is what you have to be able to do. Now the subscripts, which again show up in the formula, and we've already talked about this, we're just going to review it quickly. We use the lowest whole number ratio. So we've already discussed that at the beginning of this section when talking about how to determine the formula of an ionic compound. That's still true. You want to make sure that in the formula, the subscripts have the lowest whole number ratio for the two ions. Okay? And there's nothing else you do then in the name of an ionic compound. You just have the metal and the nonmetal. That's it. No prefixes on the names, no suffixes, except for the IDE that you put on the anion. All right, so let's look at just a couple examples. If we have MgCl2, if you write out the ions that this comes from, that's Mg2 plus and then 2 Cl minuses. But again, the way we name this is we just start with the name of the metal. Mg is magnesium, that's in the first 36 elements, so you'll need to know that. And then Cl, that's chlorine, and so it becomes chloride. All right, and again, we don't have to indicate how many of each ion are in the formula because the charges of the ions, which we can predict from the periodic table, will determine that. So magnesium chloride is always going to be 1 magnesium and 2 chlorines because magnesium is always +2 based on it being in the second column of the periodic table. Chlorine is always -1 based on it being in the second to last. So we don't need any prefixes or suffixes to indicate the numbers of each ion. And then similarly, if we have CS2O, this has O2 minus, which is oxide, and then the metal is CS. I guess this is beyond 36, so you wouldn't have to necessarily memorize this one. But CS is cesium, and then the atom name is oxide. So this, again, would usually be done in a multiple choice context, so this would be the correct name of that. It wouldn't be cesium oxygen, it wouldn't be dicesium oxide, it would just be cesium oxide for an ionic compound. And remember, the way that we recognize ionic compounds is it's a combination of a metal with a nonmetal. So that combination together tells you that it's ionic, and then we're going to follow these rules for naming. And then some other ways that we could ask these would be, give the formula and the name for the ionic compound formed from these two elements, where we give you the names of the elements, and now you have to figure out their formula. In this case, these are heavier elements, so we would indicate that strontium is Sr and iodine is I. Those are beyond what you have to memorize on the periodic table in terms of names and symbols. So if we go to the periodic table and find those, Sr is here, so that's in the second column of the periodic table, which means it will always form a +2 cation. And then iodine is over here. It's in the second to last halogen column, halogen group, so it forms -1 anions. So the two ions are going to be, and this is sort of a review of things we've already covered, Sr2+, which is in the second column, I- in the second to last column. And again, to get the formula, we just cross the charges over to make them subscripts. So the correct formula for this is Sri2, and the correct name would just be the name of the metal, which is strontium, and then the non-metal with an IDE ending, so strontium iodide. Okay, so again, for ionic formulas, we don't need to put any sort of prefixes to indicate how many there are. And then for sodium and sulfur, quickly, sodium is here. By now you should know that that's in group 1A, which is the alkali metals, so that's +1 cation. And then sulfur is over here in group 6, so it would gain 2 electrons and make a -2 anion. And so those are going to be the two ions in this formula, which would be Na+, S2-. We cross the charges and make them subscripts. That's the sort of no-brainer way of getting the formula. And we get Na2S is the formula. And again, the name is just the metal, sodium. Non-metal would be sulfur, but we change the ending to IDE to make it sulfide. Okay, so that's all there really is, for the most part, to naming ionic compounds. So for simple ones that are in the main group, the ones that use group 1 and group 2 cations from the first two columns of the periodic table, or any of the common nonmetals as anions, that's all there is to it. Now, the rules become a little bit different with transition metals. Those are the metals that are in the middle part of the periodic table, the 3D, 4D, and 5D rows of the periodic table. And also for some of the main group metals, so indium, thallium, tin, lead. So for the metals that occur in this part of the periodic table, or the few P block metals that we have over on the left side of the staircase over here, indium, thallium, tin, and lead, all being sort of main group metals that are on the right, towards the right side of the periodic table, but still metals. In those cases, there's an additional rule that comes into play. So they're very similar, there's not a huge difference, but the only difference is that these metals, the transition metals plus these few from the P block, can form more than one different cation. So you can't just use the position in the periodic table to say this metal will always form a +1 or a +2 charge. In these cases, they're variable. They can have sometimes a +1 and a +3, or a +2 and a +3. And there's no way for you guys to predict that. We don't expect you to know all of those necessarily. But the reality is that these can have different charges in the metal part, in the cation. So you have to be able to distinguish that in the formula. So the formula has the exact same convention. So we don't have to do anything different in the formula of the compound. It's just cation, then anion, lowest whole number ratio. But the only difference is that the name needs to indicate what the charge on the cation is, because in these compounds, the cation, the metal part, can have different charges possibly. There's more than one possible value, and so you need to indicate that with a Roman numeral. So in the name of an ionic compound that includes a transition metal or a few of these main group metals, there's a Roman numeral in parentheses that denotes the charge. All right, so for example, if we have an ionic compound that includes iron with a 3+ charge, again, there's no easy way to predict that this would be one of the cations for iron just based on the periodic table, but that is one of the possible charges for Fe, 3+. So when we put that in the name of the compound, it will be written as iron with a Roman numeral 3 in parentheses, indicating that it's iron 3. All right? And then for iron 2 plus, if that was in an ionic compound, that part of the name would be written as iron 2 with a Roman numeral in parentheses. So we only need to do that for, again, the middle part of the periodic table where the metal's going to have more than one possible charge, and the name needs to include include the charge so you know what that is, because then that's how you would get the formula then, because these could have two different formulas depending on the charge of the metal cation. Now there's also some common names. I don't think we're going to hold you responsible for these, but just so you're familiar with what they are. If you see them in older textbooks or maybe in the lab course, you might come across this from time to time. So just so you're familiar with it, it's not going to be included, I don't think, in our homework assignments or exams. But in many cases with transition metals, you have two or sometimes more than two possible charges. Usually it's two that are most common. So the one that has the higher charge would have an IC suffix in the common name. So if you have an Fe3 plus, that would be written as sometimes ferric, where ferrum is the Latin root of the name that gives us the symbol Fe, Ic for the higher charge, and then whichever cation has the lower charge for that metal, which in the case of iron would be a +2, is very common, also has an OUS suffix. So if you have Fe2 plus compound where iron is in a +2 oxidation state, or sorry, +2 charge, we should use that word for now, that would be ferrous. And so that's just, so there's really two ways of indicating it. These are a little bit archaic, but you'll still see them from time to time. So if you have iron 3 chloride, so that'd be iron with a +3 charge paired with chloride, you could write it as either iron 3 chloride or you could write it as ferric chloride. You might see that sometimes. But if it's iron 2 chloride, which is FeCl2, that can be written as iron 2 chloride or ferrous chloride. And now that you understand what ferrous means, you can tell me what is the name of an inorganic chemist's favorite carnival ride. Yes, so now you remember that one forever. So that's a Ferris wheel. And so those are some names that, again, I don't think we're going to test you on those, but if you see them in chemical literature or lab courses or wherever you might come across them, just know that they refer also to the charge of the metal in transition metal compounds. Now the next thing you have to deal with in naming some ionic compounds are what are called polyatomic ions. And there's a whole list of these in table 3.5 that we expect you to be familiar with. So we've already seen these in the context of Lewis structure. So NO3 minus was the example we gave you, which is nitrogen, 3 oxygens with an overall minus charge. That's an example of a polyatomic ion. So a polyatomic ion are groups of covalently bonded atoms that have an overall charge. So they can also then be part of ionic formulas because they can pair with other cations or anions to make ionic formulas where you still have just electrostatic interactions, cations, anions pairing together in the formula. So they're groups of covalently bonded atoms that have an overall charge. And you'll see them sometimes given in parentheses as well. So if in the formula of an ionic compound that includes a polyatomic, if there's more than one polyatomic ion in the formula, you're going to usually enclose it in parentheses, or you always should. All right, so this is just to familiarize you with how these are going to be shown in formulas. And the subscript that indicates how many of that ion there are in the formula is going to be outside the parentheses. So as an example, if we have sodium, which is +1 cation, a regular old metal cation, one of the polyatomic ions, which we've already seen today, is, as I said, NO3 minus, which is called nitrate. You'll need to know the name of that for the nomenclature part of this course. The formula for this compound, it's just a +1 and a -1 cation and anion, so you just need one of each to balance the charge. So you could just write it as NaNO3. One cation, one anion, that's how you would write that formula typically. But if we had calcium 2 plus with NO3 minus, to balance the charge of this, we need to have 2 NO3 minuses for every 1 calcium. So the correct way to write this formula would be 1 calcium with 2 NO3 minuses. So we're going to put NO3 in parentheses and then put a 2 on the outside. So this means we have 2 entire NO3 minuses as part of this formula when the number goes outside the parentheses. And we need that because we have to balance the charges, plus 2 from the metal, 2 minus 1s from the NO3 minuses. So you don't want to write it as, and you can see why this is confusing, right? If we just write it as CaNO3 that looks like NO32. That's very confusing, so we don't want to do that. Or we don't want to write it as CaN2O6. Technically, that's the formula, but that obscures information about what's actually in the formula, which is these NO3 minus anions. So this would be the correct way of writing the formula for that compound where you have 2 of those polyatomic anions. Okay, so let's just give a few examples then with transition metals and polyatomic ions. So if we have Fe2O3, we have to first figure out to name the compound. So Fe is one of our transition metals here. So if we're going to name this compound, we have to include the charge of the metal in parentheses to tell us what that is, because again, these transition metals can have more than one possible charge. So just naming the metal, it's not going to give us information about that. All right, so if we look at the structure here, or the formula, Fe2O3. So we have 2 irons, we have 3 oxygens. Now oxygen, its charge is going to be invariable. So oxygen is here in group 6. Oxygen will always form -2 anions. It gains 2 electrons to get to the noble gas configuration. So the oxides in this formula have 2 minus charge each. So if we have 3 -2 oxygens, what does the charge on iron have to be to balance that out if there's 2 of them? Plus 3, right? Yes. So a little bit of quick algebra there. So now with 2 plus 3 irons, we have +6 from the metal, -6 from the nonmetals, and they're balancing out. So from this formula, Fe2O3, we can deduct that iron must have a +3 charge for those to be all balanced. So then the way that we would name this is iron with a 3 in parentheses, and then the name of the nonmetal is still just oxide. Okay, so we don't do anything to the nonmetal, I mean just for transition metals, we add the parentheses to show you the charge on the, all right, and then for this one here, copper sulfate, to be able to do the formulas that involve polyatomic ions, you need to learn what they are and what their charges are. So for SO4, we would recognize once we learn all the polyatomic ions in table 3.5 that SO4 is a 2 minus charge sulfate anion. It's always going to be -2 as a polyatomic ion. And there's not an easy way to rationalize that, but that's what's going to be for us once we learn all those. So we have SO4 2 minus, and then we have copper as the metal. You don't need the parentheses here, but you will sometimes see them. There's only one of them, so you could leave the parentheses out. It could just be written as CuSO4. So you might see it both ways, but the parentheses don't need to be there. But nonetheless, if we have a 2 minus anion, what does the charge on the metal have to be to balance that? +2 to balance the charges. So we would write this as copper 2 sulfate, because again, copper is in the transition metal series. It can be either +1 or +2 very commonly, and so we have to indicate in parentheses what the charge is. Because if we just gave the name without the charge indicated, we wouldn't know what the ratio of the cations and anions has to be in the formula. So if you name these without the Roman numerals, you wouldn't be able to take that name and then convert it back to a formula. You'd lose that information, okay? So that's important for transition metals. And then for the other ones here, for these ones, we just need to know, again, the names and the charges of the different polyatomics. So chromium 3 permanganate. So chromium 3 tells us directly that it's Cr3+. So that's the nice thing about the names of transition metal compounds. If you're given the name, the charge of the metal is directly stated, so you don't have to look it up or try to figure it out in any way. It's chromium 3+. But then permanganate, we have to know, is the anion that has the formula MnO4 with an overall -1 charge. So there are 2 polyatomic ions that we'll see, or maybe 3, but there's 2 that are similar, that have metals at the center. So permanganate is MnO4-, chromate is CrO4-2-. Those are 2 of the ones on the table. But if we have 3 plus on the metal and 1 minus on the anion, we need to cross those. And so the correct formula for this would be 1 chromium, the -1 charge on permanganate becomes a subscript of 1. Then we need to have 3 of the MnO4 minuses to balance the charge overall. So that would be the correct formula for chromium 3 permanganate, 3 MnO4 minuses to balance the charge. And then tin 4 chloride. So tin is Sn. And if it has a +4 charge, chloride, as we've seen many times already, is Cl-. So to balance the charges, again, the simple way is to just take the charges and cross them over and make them subscripts. That leaves us with 1 tin, 4 chlorides that will balance the charge completely, and this would be the correct formula then for tin 4 chloride. So we'll ask you to go both ways, name to formula or formula to name. And then the last type of compound, we probably won't finish everything today, but we can at least cover the simpler ones, are covalent compounds. So for covalent compounds, you need the prefixes included in the name to tell you how many of each atom you have in the formula, because they can combine in many different ratios. So we've already seen that, right? With carbon and oxygen, you can have CO, you can have CO2. Both of those are possible formulas for carbon and oxygen. So just calling it carbon oxide doesn't tell you what the formula is, because for nonmetals on the right side of the periodic table, when they form covalent compounds, in many cases they can combine in different ratios. We saw that with law of multiple proportions way back when. So we have to have prefixes in the name that tell us how many of each atom there are in the formula. So we're going to go from up to 10 is the highest we'll go. So the prefix for 1 is mono. You only use this on the second element in the formula. So if there's only one of the first element in the formula, you don't have a prefix at all. So if you don't see a prefix at all, that means there's 1. But if you see mono, which would be often on the second element, then that indicates there's 1 of that. So for example, carbon monoxide, mono means 1, oxygen. And then we have for 2 is di, 3 is tri, 4 is tetra, and penta, hexa. This one is usually hepta. Sometimes you'll see it as septa, but hepta is more correct. And then we have octa for 8, nona, and then deca. So if you know Latin, these are probably easy, but most people don't know Latin, so you'll have to learn them. But they're pretty familiar. You've probably seen these in other contexts outside of chemistry. So mono, di, tri, tetra, penta, hexa, hepta, octa, nona. Sorry, nona's with an A, and then deca. All right. And then sometimes we leave the vowel off if the element that it's attached to also begins with a vowel. So that's why we would see monoxide instead of monooxide. So sometimes the vowel is left off, but again, these are all multiple choice questions, so don't need to bore yourself with those fine details. So these prefixes are going to apply to a class of compounds that are called binary covalent compounds. So these are the only, this is the major type of covalent compound we want you to be able to name in this course. If you take organic chemistry, you'll learn about nomenclature for all kinds of other things. But binary covalent compounds are fairly simple. They just have 2 and only 2 elements. So binary means 2, and it means that the whole formula has just 2 different elements in it. So the rules for nomenclature, typically speaking, you're going to be given the formula and have to give the name, and you just name the elements in the order that they're in the formula. Now, the convention for what order they are presented in, if you're curious, is that the element with the lower group number comes first. So again, group number is which column in the periodic table it's in, and so that's going to be the one that's named first. Which again, back to the familiar example, is why it's carbon monoxide, carbon dioxide. Carbon is group 4, oxygen is group 6, so the element with the lower group number is first. But you don't usually need to worry about that because again, you're going to be given the formula and you just have to produce the name with the elements in the same order that they're in the formula. And they're all multiple choice anyway. Now, if the 2 elements are in the same group, like let's say the SO3 example we gave earlier, which is sulfur and oxygen, the higher period comes first. That's the one that's further down in the periodic table. So for sulfur and oxygen, SO3, sulfur is in the 3rd row of the periodic table, 3rd period, oxygen is in the 2nd, so you would name sulfur first. It'd be sulfur trioxide, and that's why the formula is also written as SO3. So those are the conventions, but like I said, they're not terribly important because usually in the context of the problem, it'll be obvious what order the elements need to come in, but we do still put an IDE ending on the second element. So even though we're not really forming ions in these compounds, these are all covalent compounds that we're dealing with, you still use the IDE ending on the second element. So again, carbon monoxide, not carbon monooxygen. Now again, the only major difference between ionic formulas is that you use the prefixes to tell you how many of each atom there are. So ionic formulas never use prefixes. We saw that in the several examples we gave of ionic compounds earlier. But for binary covalent compounds, you need to have prefixes to tell you how many of each atom are in the formula. And the formula is not going to be reduced to the lowest whole numbers. All right? Because again, in this case, the formula is going to tell you how many of each atom are in a single molecule of that compound, and it's not necessarily the lowest whole number ratio. So we leave the formula as is, as it comes directly from the name. So as an example, NO2 and N2O4 are two different compounds. So we would not want to take the formula for N2O4 and reduce it to NO2, which is the lowest ratio. All right, so very often you're going to have covalent compounds where the ratios of the two elements are not the lowest whole number ratio, but that's fine. You never want to change those for covalent compounds because that gives you specific structural information about the molecule. So what this means is that one molecule of this compound has 2 nitrogens and 4 oxygens. And that's a totally different compound than the one that has one nitrogen and 2 oxygens. So don't reduce the formulas in the case of covalent compounds. Write them exactly as they're given from the name. All right, so let's just do a couple examples of these and then we'll save acids for next time. So if we have SF4, S is sulfur, and 4 is fluorine. So there's 4 fluorines in the formula, so the prefix that corresponds to 4 is tetra, and the second element gets the IDE ending. So it's sulfur tetrafluoride. Remember, we don't say monosulfur tetrafluoride. We don't use mono if it's for the first element in the formula. All right, so you wouldn't say monosulfur tetrafluoride, it would just be sulfur tetrafluoride. The first element, if there's only one of them, you just name the element and then the mono is implied. For P2O5, it's the 2 tells us that we need a di prefix, the 5 tells us that we need a penta, and we name the elements in the order that they are in the formula, which is, so phosphorus first, so it's going to be diphosphorus because there's 2 of them. I can never spell phosphorus right, but I think that's right, O-U-S. And then oxide, there's 5 of them, so that's going to be pent. Now remember, if the element that is modifying begins with a vowel, you often leave the vowel off the prefix, so it's not usually written as pentaoxide, it's written as just pentoxide. But we would not, again, count you guys wrong for that, because that's a really silly minor rule. But pentoxide is how you more commonly see it, where we leave off the A, because oxygen also begins with a vowel. And then taking names to formulas is actually quite easy for covalent compounds because you just have to remember the prefixes. And so nitrogen is N. There's no prefix on that, so that tells us there's 1 nitrogen. And then trichloride, 3 chlorines, NCl3. All right, so binary covalent compounds I think are pretty straightforward for most people because there's only a couple rules and it's converting between names and formulas is usually pretty simple. And then for disulfur decafluoride, disulfur, S2. Decafluoride, fluoride is fluorine, which is F, deca is 10, so it'll be S2, F10. All right, so that's binary covalent compounds. So the last thing we'll have to cover from chapter 3 next time is naming acids, which is a little bit more complicated than covalent compounds, but there's only a couple different categories you have to worry about. And then we'll move on to chapter 4 after that. So we're getting very close to being done with all of the exam 1 material. So as of next Tuesday, you'll be all set on that. And you can start your final reviews for the following week's exam. All right, I'll be in my office right after class if you need to come see me about anything. And if not, I'll see you guys next week.
I'm like really confused as to how you found out these.
The charges on the
Yeah,
metals?
the charges on the metal. And
So
then
that's from the formula. So in the case of a transition metal, you can't just look at the periodic table and figure out what it is. You have to look at the formula of the compound that we give you. So if you're doing it formula to name, look at the formula first. And you know that so these ones here. So the anion charge is not going to be variable. So all the anions that we have to worry about, either the ones that form from the nonmetals or the polyatomic anions that you have to learn in that table, their charge is always going to be the same. It never changes. So if you see oxygen in an ionic compound, that's always going to be -2.
right.
So then if you have three -2 oxygens, what's the total charge on the anions? 3 times -2 is -6. So you need +6 from the metal to balance the charge. The charge always has to be
Okay.
balanced. And so there's 2 of the irons, which means each has to be +3.
Okay, thank
So it
you.
looks like the YouTube's gonna be a little bit of a bonus.